Hello, everybody. Welcome to the IAMP seminar. As most of you know, this is a bi-weekly event of the International Association of Mathematical Physics, which is always waiting for new members. And we are very glad to have today Sky Kao from the MIT, who will speak about the global well-posedness of the two-dimensional stochastic Abelian-Higgs. So Sky, please go ahead.
Yeah, so thank you very much for the introduction and the invitation. Today I'll be talking about doing work with Bjoern Bringmann who's currently at Princeton. I should say it's mostly going to be a PDE talk today in terms of the results and the techniques that we use. I'll point out the connection with math physics when it comes. And yeah, if you have any questions, feel free to ask at any time. I'm always happy to answer questions. And let me begin my talk by discussing this classical, very fruitful interaction between geometry and PDE. So on the one hand, if your primary motivation is geometry, you can try to use PDE techniques to prove geometric statements. I mean, that's the whole field of geometric analysis. And I'm not going to talk about that much today, because between geometry and PDE, I think our main motivation is PDE. So we want to prove PDE results. And it's actually often the case that, well, geometry informs PDE. So in the sense that if you have a geometric PDE, or if your PDE comes from geometry, then oftentimes you can prove better analytic estimates than you might expect at first. The example that kind of comes to my mind directly, even though I'm not an expert in this, are these so-called null form estimates in hyperbolic PDE. And in this setting, what you have is basically a nonlinear wave equation. And, well, you want to estimate your nonlinearity. And these null forms basically say that, well, if your nonlinearity is of a very special structure called exhibiting a null structure, then you actually have estimates which are better than what you expect in the most general setting. And these improved estimates then allow you to, well, get better local and global theory results. That's the point, right? And so, yeah, this is a situation where if you have a very special type of nonlinearity, you have refined analysis. So then you might ask yourself, well, in which situations would you actually expect to see such a nice nonlinearity? I mean, have this very special null structure. And the answer is, well, if your PDE came from geometry. So it's often the case that wave equations coming from geometry exhibit this null structure, which you can then use in your analysis. Right. Another example where geometry enters into PDE or analysis, well, I wrote out these two other examples, integrability by compensation and elliptic PDE. It's kind of similar to these null form things. I won't really go into detail, and then also these diamagnetic inequalities in elliptic and parabolic PDE. And so that we'll see a bit later on, how that enters. Right, so these are maybe, I listed some examples of how geometry informs PDE. Now, what about stochastic PDE? Right, so how does geometry inform stochastic PDE? And so first of all, I mean, why is this not immediately clear? And it's unclear because the types of stochastic PDEs that I'm thinking about, well, that we mostly are talking about today are singular SPDE. So basically the solutions, they're not function valued anymore. They take values in spaces of distributions. So negative regularity distribution spaces. And so, whereas all these estimates are for positive regularity functions. I mean, so none of these classic things apply anymore. And so that's why it's unclear how geometry informs SPDE, right? But this was the conceptual question that was at the front of our minds when we began this project. And I would say through the course of this project, we were able to understand some aspects of this interaction somewhat. And what little we were able to understand allowed us to prove our global results. But I do want to stress at the beginning of the talk, there's still much more left to understand about this interaction of how geometry enters, how you actually use it in your singular SPD arguments. And I think this would help with the remaining open questions with global existence of non-Abelian YAMLs, for example. But also we just find it to be a fascinating question, which is why we wanted to think about it. Okay, so that's some beginning conceptual motivation. And so now let me just jump directly into stating our model. So it's stochastic Abelian-Higgs. So what is it? It's a coupled system of stochastic PDEs. So we have an A field, also often called the vector potential. And so our base space is always going to be T2. So I said the title said we're in 2D and we're going to work on the torus, so periodic boundary. So A is R2 valued, vector potential. Phi is this scalar field. It's complex valued. It's a function on the torus taking complex values. And so we have a coupled system of stochastic PDEs in A and phi. So in the A equation, it's basically a nonlinear heat equation, right? So we have this heat operator. And then we have this nonlinearity, which looks like phi bar dA phi. I'll say more about, okay, I'll write out the formula for this covariant derivative of phi on the next slide. But let me just give you generally what the equation looks like first on this slide. And then, okay, this is, sorry. So this P perp is the Lie rate projection, which puts you in this Coulomb gauge. So it enforces that our vector potential is divergence free. And this is nice to have because the Coulomb gauge is always best for regularity. And if it doesn't cost you anything, you may as well work in this Coulomb gauge. So that's what this P perp does. It projects you onto the space of divergence-free vector fields. And then we have the stochastic forcing psi also projected. And psi is supposed to be a space-time white noise. And it's going to be an R2 valued space-time white noise because A is R2 valued. So that's the A equation. Again, the nonlinearity basically looks like phi bar dA phi, so it has this derivative inside it. Now the phi equation, it's also a nonlinear heat equation basically, but now you have not the usual heat operator, but this so-called geometric or covariant heat operator. So I'll give a formula for this also on the next slide, but just know it's some version of a geometric heat operator. And then you have this polynomial nonlinearity, like minus phi to the q minus 1 times phi. So it's basically degree q. And then plus zeta, which is a stochastic forcing. It's complex valued space-time white noise. So these stochastic forcings are what make it a stochastic PDE, basically. And here we're going to take q to be, well, our result works for any odd integer q at least 3. So if you want, you can just take q to be 3. Maybe that's the most common example. In which case it kind of looks like 543, the geometric version. No, sorry, 542, I guess, because we're in 2D. And yeah, so that's the equation. And maybe I'll say a word about how you think about these space-time white noises, in case you're not used to thinking about it. Basically, what it is at every point in space and time, you have an independent Gaussian random variable. For psi, it's an independent R2 valued Gaussian. And then for zeta, it's an independent complex valued Gaussian. So that's what we mean by space-time white noise. The thing is, this thing is going to be too rough to think about it as a function. There's no way it's going to be even a measurable function because, I mean, the values at neighboring points are just completely, unrelated. And so the way you make sense of it mathematically is as a random distribution. So yeah, it's going to be a random distribution, which enters into your PD. Yeah. So that's our model, stochastic Abelian-Higgs. And yeah, so maybe let me give some formulas. It doesn't really matter, the precise formulas for the talk, but just in case you want to see them, here they are. So yeah, first of all, this Lie rate projection, which if you recall, puts us in the Coulomb gauge. So it ensures that our vector potential A is divergence free. Well, here's an explicit formula for it, if you wanted. And you can check algebraically that after you hit it with this Lie rate projection, you actually have this Coulomb gauge condition. But okay, so that's the Lie rate projection. And then this covariant derivative, dA phi, it looks like the usual derivative, so the gradient of phi, but then plus this extra term which depends on A. So if A is non-zero, then it's different from the usual gradient. And so it's the complex unit I times A times phi. So that's what the covariant derivative looks like. And then this covariant Laplacian, which if you recall, entered into I mean this geometric heat operator for the phi equation. So this Laplacian right here in coordinates would be expressed like so, where if you calculate based on this formula, you eventually get that the covariant Laplacian is equal to the usual Laplacian plus this kind of divergence term, and then minus an a squared phi. And maybe here, this is kind of the special case where we took A to be divergence free. In general, I think if A is not divergence free, you get some term like this, which depends on the divergence of A. But in this talk, we're always going to be in the Coulomb gauge, and so A is divergence free. So we don't see this extra term. Yeah, okay, so that's an explicit formula for this covariant Laplacian, but kind of one of the points of this talk is that you don't want to write it out this way. You want to actually think of it as a Laplacian in its own right. But I'll get to that a bit later. So any questions on the notation so far? If not, then I will just get right into stating the main result for today, which is a soft global well-posedness statement, which says that for any initial data A0, phi 0, okay, so this sort of polar Besov space of negative regularity, you don't really have to worry too much what it is. It's just for some reason the natural space of initial data for stochastic Abelian-Higgs. But for these global problems, it's less about the regularity and more about the size. So if you want, you could also just take A0 phi 0 to be smooth, if you want. Yeah, the main result is basically for any initial data in a reasonable space, the solution to stochastic Abelian-Higgs almost surely exists globally. So it's a soft global well-posedness result. In our paper, we have more quantitative bounds. So we actually bound the solution at later times. And in particular, we bound how the initial data enters at later times into the solution. But at least for today, I'm just going to mainly focus on how we prove this soft global result. And it is the case that if you work a bit harder, and do some more refined estimates, you can actually get uniform and time bounds. But yeah, okay, so that's the main result. Right, so I'm kind of going backwards here in that I kind of get right to the main result, and now I want to go back and give some maybe of the geometric background for this model. So that's what I'm going to do next. So I started my talk off discussing geometry and PDE, so let me give a few words how geometry enters into this model. And then I'll get to like the second half of the talk, the techniques we use to prove this main result. But geometrically, what we really have is, I mean, in the background, we have this line bundle, this complex line bundle. In our case, it's just trivial, so it's a product of our base manifold. It's a product bundle consisting of our base manifold and our fibers, which are just C. And you should really think of phi as a section of this line bundle. So I use this notation to denote a section. And it is just the case, in this case of a trivial line bundle, you can think of phi as a complex valued function. But geometrically, what it really is it's a section of the line bundle. And in this A, you should really think of as a connection or a covariant derivative on E, on the bundle, right? And so basically gives you a way to differentiate sections, right? It gives you a notion of covariant differentiation. That's what really A gives you. And then as soon as you have, I guess the point is that even though we took a trivial bundle, we still have non-trivial geometry. And that's really encoded in the fact that A may be non-zero. And I mean, what is geometry? It basically is curvature, right? And so in this setting, curvature is expressed in terms of this. You could think of it as a matrix of functions. You could also think of it as just the exterior derivative of A. But in coordinates, the ijth entry or function of the curvature is partial iaj minus partial jai. But okay, that's also just the exterior derivative of A. Right, and so this notion of curvature captures, in a sense, how non-trivial your geometry is, in the sense that, if you compute, I guess, commutators of your covariant derivative, you basically get a the curvature popping out, right? So that's how the curvature arises in this setting. Basically, the failure of your covariant derivatives to commute, right? Okay, so that's like 2 minutes on the geometric setup. And the point is that, as is usual or often the case in gauge theory, there's some sort of energy functional which measures how non-trivial your geometry is, right? So you can take norms of your curvature and your other things to give you a measure of how non-trivial you are. And the natural energy functional in Abelian-Higgs is this thing here, which is basically in words, the squared L2 norm of the curvature. And then this, in a sense, covariant H1 norm of the field phi. So it's basically the L2 norm squared of dA phi, the covariant derivative of phi. So you could think of it as an H1 norm in a sense. And then also this Q plus 1 norm, LQ plus 1 norm of the field phi. And so that's the energy functional. And you might ask, okay, how is this related to Abelian-Higgs? Well, the point is that if I take the gradient flow of this functional, I get exactly Abelian-Higgs. And if I take this stochastic gradient flow, I get stochastic Abelian-Higgs. So let me go back to the PDE now, which I wrote down here. And if we just ignore the stochastic forcings, if we take these out, it's a deterministic PDE. And it's actually the gradient flow of the energy functional that I just showed you. And then the stochastic gradient flow is just if you add in these space-time white noise stochastic forcings here and here, and you get the so-called stochastic gradient flow or stochastic gradient descent. And that's exactly stochastic Abelian-Higgs. And so that's kind of that's how the energy functional enters. Basically, you take the gradient flow. And that brings me to, one of the motivations you want to study this stochastic PDE. From one point of view, it's just, okay, it's a PDE and you added in randomness, but why, right? One motivation is because it is supposed to be related to the formal invariance measure, which is basically given by e to the minus this energy functional, right? And in math physics or constructive quantum field theory, this measure is the thing you want to study. And this in recent years, this program of stochastic quantization, where you study this measure by looking at the dynamics, say, or some other Gaussian source of randomness, it's kind of, well, people have been studying, using stochastic quantization in recent years to study measures of this type, right? And so that's one of the main motivations to study stochastic Abelian-Higgs, because it's related to this, I guess, Euclidean quantum field theory, this invariant measure, which is something you would want to study from the math physics point of view. I should say that for Abelian-Higgs in 2D, the measure itself has been constructed a long time ago, like 40 years ago, by Bridges, Froelich, and Zeiler. So yeah, this measure has been constructed, but so our global result gives a new construction, I would say. So that's via stochastic quantization. But another motivation, and I think this was more our motivation for studying it, is that we think that it's an inherently interesting PDE problem, which, because it involves this interaction between geometry, probability, and PDE. So when you study singular stochastic PDE, you already have to have this interaction between probability and PDE. You need insights from both fields to solve your problems. But now when you have these geometric PDE, or these PDEs that come from geometry, then you have this additional geometry component that you have to understand. And that, I think, we found it really fun to understand, even though neither of us are really geometers, but it's been fun to learn some more geometry in the course of this work. Right, so these are maybe the two main motivations to study stochastic Abelian-Higgs, depending on your tastes. Yeah. And so now, before I get into some details, let me just very briefly go over the history of the PDE side. So I already mentioned like the Bridges, Froelich, Zeiler paper, which constructs this measure. So I'm going to focus more on the PDE history. So if you just look at the deterministic PDE, so without the stochastic forcing, you can look at a more general model, which is called Young-Mills. It's where you have a non-Abelian gauge field instead of this like R2 valued vector potential. And for the PDE, at least in 2 and 3 dimensions, local and global existence is very classical by now. I mean, it was done probably, okay, maybe the 80s, I would say, by Rade. So maybe I'll write that name down. So in 2 and 3 dimensions, he was able to prove local and global existence for initial data in the natural space, H1 in 3D, I guess. And so the point is that it's like 40 years old by now. But then as soon as you add in the stochastic forcing, we didn't actually even know how to do the local theory until 10 years ago. Right? So for 40 years, we've known how to do local and global theory for the deterministic PDE. As soon as you add in stochastic forcing, things become, I mean, so irregular that we just didn't know how to handle that until 10 years ago. And that was with, you know, these breakthroughs of regularity structures, and para-controlled calculus, or para-controlled distributions. So Martin Heyer and Gubinelli and Keller-Prokowski actually allowed us to prove local theory, or prove local existence for a wide class of stochastic PDEs, which are subcritical in some sense that I won't get into. So that was 10 years ago. And then finally, in the past couple of years, this local theory technology was applied for Young-Mills, and actually more generally Young-Mills-Higgs, which again is like maybe the most general possible model you can look at in the setting of Young-Mills. When you have a non-abelian gauge field and as well as this phi field, this Higgs field, and they were able to show in 2 and 3 dimensions local existence and gauge covariance. And so the point is that, okay, local existence basically would have followed in the 2010s from this very general theory. So I would say the main thing was showing this so-called gauge covariance. And in a sentence, it's basically that you have a geometric PDE and you want to show it transforms naturally under changes of coordinates. And in the context of gauge theory, changes of coordinates are known as gauge transformations. And so you want to show gauge covariance in the sense that you transform naturally. And under these gauge transformations, and that was the thing that needed to be shown. And that took quite a lot of effort. And so, yeah, these two papers by Chandra, Shavira, Pyre, and Shen were able to show local existence and gauge covariance in 2 and 3 dimensions. So that was within the past 5 years. And then more recently, there was this paper from 23 by Chevirev and Shen that showed global existence for 2D stochastic Young-Mills. And then there was our work which showed global existence for stochastic Abelian-Higgs. So I do want to compare and contrast these two works, because in a sense, these works are both more general and less general relative to each other. So the first work is more general because they consider Young-Mills, so even the non-Abelian case. But it's also less general because they don't look at a Higgs field, right? So it's Young-Mills, not Young-Mills-Higgs. Whereas we have this Higgs field here. And so their technique is that they kind of start on the lattice, look at the dynamics on the lattice, and then show that you have a scaling limit as you send the mesh size to 0. And kind of they're using Bourgain's globalization argument to get the global existence. And then this Bourgain's argument kind of requires knowledge of the measure, the invariant measure. And so the reason why they work with Young-Mills and not Young-Mills-Higgs is because the 2D Young-Mills measure, in a sense, is kind of exactly solvable. We know a lot about that measure. We can write down laws of all the observables. And so it's a very special thing, whereas we don't know as much about the Young-Mills-Higgs measure, even in 2D. And so that's the reason why they look at stochastic Young-Mills. In our work, we try to use mainly PDE arguments and as little knowledge about the invariant measure as possible. And so we don't use Bourgain's argument. And so that's why we're able to handle the Higgs field. But at the moment, we don't know how to handle the general non-Abelian Young-Mills case. Because there are some simplifications when you look at an Abelian setting. So yeah, that's all I'll say about that. And maybe I should stop and ask if there's any questions before I go into the details. Yeah, okay, so then before I get into how we do the global theory, maybe I want to review very quickly how you do the local theory, because the basic setup does enter. And so, yeah, let's review in 2 slides how you do local theory for stochastic Abelian-Higgs. So what as you always do in these singular SPDEs, is you isolate out the linear part. So the solution to the linear equation, and it gets your noises, your stochastic forcings, and then you write your full solution A and phi as the linear parts plus a nonlinear remainder. So that's what I'm writing here. And what you want to do is you want to set up a fixed point problem for x and eta, right? Because local theory for PDEs, even singular SPDEs, you always view your solution as the equation to a fixed point problem, and you get it by Picard iteration. And in this setting, you have to isolate out the kind of roughest part, this linear part, and set up your fixed point problem for the remainders. That's just the setup, how it's done. And then to set up this fixed point problem, you have to write out the equations that these remainders solve. So I wrote it out here. The exact formula of the equation is not so important. I mean, it's important for the paper, but at least for this talk, you don't really have to worry too much about, the exact form. But I wrote it out anyways. And so the point is that, okay, because these things are explicit probabilistic objects, so here's where here's where you need to do probability theory. You have to bound these objects, or these linear parts using probability theory, because they have this stochastic forcing, which is Gaussian, which you know everything about. And using probability theory, you can show that these objects, they're in this space. So basically, they're continuous functions in time, but taking values in a space of distributions in space. So they're distributional in space. They take values in this this negative Holder space. You can think of it as a generalization of the Holder space to negative regularity. So that's the Cx minus kappa. And yeah, so this is just going to be true by probability theory. So that's one aspect of it. But now here you have to, on the remaining system, you have to do analysis. And this is where classical Schauder estimates come in, which is, okay, if you have a heat equation of this form, well, then I can at best expect my solution x to have 2 more degrees of regularity than the right-hand side, right? Because the solution x, I'm taking a Laplacian and also a time derivative. So in terms of space, x is supposed to have 2 more degrees of regularity than whatever is on the right-hand side. And in terms of time, 1 more degree. But yeah. And so what that means is kind of, if I look at the right-hand side, at best, the most singular term, for instance, is this term, like this object, D object. Okay, I'll call this the phi linear object. So the phi linear object, D times its derivative, this at best has spatial regularity -1, minus kappa. Because here I take a derivative that's something at regularity minus kappa. That's put me at -1 minus kappa. And then I have to worry about if I can actually multiply these 2 distributions, which it turns out you can because these things are explicit objects. But at best, the regularity of the right-hand side, I'm saying is this, -1 minus kappa. And now Schauder is going to tell me that x at best has regularity 2 better than that, right? So that's what I'm saying here. X at best is going to have this regularity here, 1 minus kappa. And similarly with this eta term here, because again, maybe one of the worst terms on the right-hand side is this. If I look at this term here, I have as one of those terms, this derivative here, which also is at the same regularity, -1 minus kappa. And so again, similarly with eta, at best, eta is going to have 2 more regularity, and that's going to put me in this space. Right, so this is a type of formal power counting that you often do to do local theory for a singular SPD. Right? But then here's the problem. Here's why it was so hard to even do local theory. You run into this problem that, okay, if eta is at regularity 1 minus, then I cannot define this product, which, for instance, appears here. So I have this eta bar times the derivative, or sorry, I have this phi linear object bar times the derivative of eta. which is what I'm writing out here. That's one of the terms on the right-hand side for x. And I cannot define this if eta is only is at regularity below 1, so 1 minus kappa, and this is at regularity 0. Because I can't, in general, multiply two distributions. I mean, distributions of negative regularity. Right? And so, yeah, okay, so this is a problem. You run into this problem. And then, okay, to get around this, you have to either use regularity structures or pair-controlled calculus, or I guess the flow method, to actually be able to close your fixed point problem and do local theory. And in two sentences, I mean, this is not the point of this talk because we're going to be doing global theory, but I'll just say two sentences why you can get around the problem using these techniques, which is, if you can't close your fixed point problem when you expect you should be able to, that just means you're not assuming enough about your solution. Like you need to have more detailed ansatz for what your solution looks like. And what your solution looks like, basically, this problem of multiplying two distributions, it's a problem at the smallest spatial scale. And the point is that at the smallest spatial scales, your eta actually looks like some explicit probabilistic object. And that's kind of encoded in how you set up the problem using regularity structures or pair-controlled calculus. That you have to make a finder ansatz for what eta looks like at the smallest spatial scales or the highest frequencies in Fourier space. And the point is that at the smallest spatial scales, eta looks like a Gaussian object. And for instance, if I had written this type of object, even though this object suffers from the same issue in terms of I can't multiply two distributions, I can still define this using probability theory. And something similar is going to happen with this product because it turns out eta is not just some arbitrary distribution at the smallest spatial scale. But you have to put that in your ansatz. So that has to all be part of your fixed point problem. But okay, so that's some general idea of how you get around this problem using these techniques. And that's kind of a quick review of the local theory. And so now I want to spend the rest of the talk discussing how we do the global theory. But we will use in the end that once you're able to close your fixed point problem, your solution will look like this. Like it will look like this explicit object, and then plus a smoother remainder, which is in this space. It's just how you actually close your local your fixed point argument for the local theory. You have to do something extra. But in the end, you will have this decomposition for your solution. Okay, so that's the local theory. And yeah, one point I want to make is that the local theory was very insensitive to the exact details of the equation. I could have changed the equation by some way, but the point is that as long as I have a nonlinearity that looks like phi d phi, any nonlinearity that looks like this, you're going to be able to handle by the exact same arguments in the A equation. So recall this is kind of the nonlinearity that enters into the equation. So morally, the A equation looks like something like this plus psi. Up to these Lie ray projections. And it didn't really matter exactly the form of the nonlinearity. You're going to be able to handle it as long as it's of this phi d phi form. So this quadratic with one derivative nonlinearity. But this is not going to be true of the global theory. The global theory definitely depends on what your equation looks like. This is just true even for deterministic PDE, right? And in the end, in the deterministic setting, you're going to have global existence because if you recall, the Abelian-Higgs equation is the gradient flow of some energy functional. So if I go back all the way here, so if you recall, if we take the gradient flow of this energy functional, I get exactly the Abelian-Higgs equation, so without the stochastic forcing. And in the deterministic setting, that's kind of the reason why you get global theory, because you have this energy functional, which is always going to be decreasing along your flow. And then you just try to control your solution in terms of the norms that you control. And that's kind of why the Coulomb gauge is good because, I won't get into it. But basically, this this norm, I mean, this functional is going to control your solution. And then you just kind of iterate. But yeah, so in general, to do global theory, you have to care about the exact details of your equation. And that's where geometry is going to enter, basically. And so, yeah. So as a first attempt, okay, how do you, I mean, what's one general approach for doing global theory? You just try to do energy estimates, which kind of means you try to compute the evolution of your solution and try to just bound the growth of say the norm of your solution, or the norm squared. And so let's just try to do that. I mean, that's what you would do in the deterministic setting. But we're going to have to do it for the remainder because well, kind of if like okay, if we want to say something about, for instance, this energy functional, we cannot do it for the whole solution because the whole solution is at negative regularity, right? Because we have this, I mean, this thing definitely requires phi to have regularity 1 because I'm taking the derivative and taking the L2 norm of the derivative of phi. But you see in the stochastic setting, phi looks like this, and this is at regularity 0, or 0 minus. Kappa is some small parameter. So I have no hope of controlling the energy for the whole solution itself, right? Because of this most rough or most singular part, right? So the only hope I have for doing energy estimates is on the smoother remainder. So that's what we're going to do. And that involves computing the evolution of the remainder. And then testing, eta against itself, against the equation. And so, okay, again, like it doesn't really matter the exact details of the equation for eta, the remainder. The main thing is that now if I compute the evolution of eta squared, I'm going to get some good terms, but then I'm going to get one really bad term, which I highlight in red here. Why is this a bad term? It's bad because it's quadratic in a squared. And that is going to, I mean, that just gives us problems for controlling the evolution for a long time scale, right? Because we have to control eta and we have to control a. Well, in terms of x, I guess. We would do something similar for x, where we would write out the equation for x and try to control the evolution of x squared, or the norm of x squared. But if I already have this quadratic dependence on a, that's just there's not gonna be any hope in being able to control this for a long time. Basically, if this were an a to the 1, so if I just had linear dependence on a, then we would have hope. Then it almost behaves like a linear equation. And linear equations are relatively easy to do global theory. But as soon as you have some higher power than 1, in our case a squared, we really don't know how to get around this. I mean, this caused us problems too. I mean, the main point was how you remove this dependence, this quadratic dependence on a. And so, yeah, that's what I write here. We cannot absorb this. I mean, we just couldn't, no matter how we try. Right. And so that made us reflect. Now, this a squared arises because we defined this bilinear object like so as the solution to the stochastic heat equation, as you always do in the local theory. I mean, this is just what's always done in the local theory for singular SPDEs. You lay out the most irregular part, and you put that in the solution to the linear equation. Right? You put your stochastic forcing into this linear equation, and you call this your linear object. Right? That's just what you always do. But somehow in this geometric setting, that's not the right thing to do. And this led us to, I mean, one of our first main ideas, which is, okay, why not define a modified object? Which satisfies this equation. So I call this CSHE, so for covariant stochastic heat equation, because you have this geometric Laplacian instead of the usual Laplacian. So if you recall, way back, the Abelian-Higgs equation, maybe let me try to skip back there. The phi equation has this geometric Laplacian, right? I kind of mentioned this in the beginning. Whereas when we were doing local theory, and this is again what you always do in the local theory, you define the object using this Laplacian. And I'm saying basically that's not a good idea. What you really want to define this object as is using, well, you want to define it using not this heat operator, but the geometric one. Right. So now let's go back here. And okay, so I wrote out this covariant stochastic heat equation. To make notation less confusing later on, we're going to replace A by B in the above, and we're going to choose B. We're going to choose B later on. Because later on, for reasons I'll talk about, we can't actually use A here, but we can use something else other than A, and that ends up being good enough. So let's just replace A by B, where B is some, again, what is B? B is a time-dependent vector potential. So for now, let's take B to be a general function of time and space, taking values in R2. So it's a time-dependent vector potential. And let's look at this equation. I mean, it's a linear stochastic heat equation, so it shouldn't be too hard to bound, right? And so again, so this led us to the following subproblem, basically. Let's forget completely about stochastic Abelian-Higgs for the moment, the problem that we started with. Let's take B to be just some deterministic function, some space-time, some time-varying connection, or vector potential. What kind of bounds can we hope for on this equation? And maybe one thing I should have emphasized was that you'll just have to believe me that the algebra works out that if we did take this as our new linear object, and then we decomposed our solution phi in terms of the linear object plus eta, then in the eta equation, we would no longer see this bad term. So, okay, sorry, I should have emphasized that. I mean, that's also the whole point of working more geometrically, in that if we use this more geometric object, then we kind of get around this difficulty that we couldn't get around before. That was the point of this, right? And so, I mean, that's again, the point of this talk is that geometry is informing singular SPDs, and this is the first entry point of that. And so, yeah, again, you'll just have to believe me that this bad term only arises because we didn't use this object. And then, so, yeah, so what bounds on this equation can we hope for? So we have this subproblem now. Just forget about stochastic Abelian-Higgs. How do we bound this? How do we control it? So let me tell you what you don't do first. What you don't do is, I mean, this is what we did at first, of course, because I mean, we were trying, it was not clear to us at first how you do this. Because, okay, again, like I said, we're not geometers, so we're not that used to thinking about this type of covariant heat operator. So our first instinct, and this is again also what you always do in local theory, is you just expand this out. You forget the geometry and you just write it as the usual heat operator and then plus the extra terms. Okay, so if I expand out the formula for what this geometric or covariant Laplacian is, I'm going to get exactly this equation. Because to leading order, it's a Laplacian, so it has this Laplacian part, but then you have these lower order terms. So this derivative and then this polynomial nonlinearity. Right? But the point is, once you do this, you just loop. Because the whole goal is to avoid dependence on B as much as possible. Like, this was the problem for us, this quadratic dependence on A, which I'm now calling, well, now it's B, right? But now I just see it again here. Like, and so we have to avoid this somehow. I mean, once you do this, you just lose. So once you do this, right? So yeah, you don't do this. And again, like this is not something you would ever do in geometry. You would never, ever, ever expand out this Laplacian into coordinates, right? You just don't do this in geometry. So if you think geometrically, actually the answer to what you should do becomes actually kind of clear. And it's actually a very simple idea. Instead, you just write this object in the following form. So first of all, I can write it as basically an integral against the right kernel. And the point is that, okay, if zeta were actually smooth here, if it's actually a smooth function, then I just have a linear equation, right? A linear equation with some sort of smooth forcing. Then I know how to write down the solution. I just use the kernel, right? So this PB is the covariant heat kernel, as I call it. Right? It's basically the integral kernel for this operator, or the inverse of this operator. I mean, this is just the general formula for solutions of linear equations. You can always write it as, I mean, assuming the kernel exists, you can just write it as in this form, right? Assuming zeta is smooth. In this case, zeta is not smooth. I mean, it's space-time white noise. But the point is that this type of integral against space-time white noise, we know how to control using probability theory. In the sense that this is just a property. This is kind of the definition of space-time white noise. If I want to estimate the second moment of this random variable, it's just going to be the L2 norm squared of the thing I'm integrating the noise against. You can take this as the definition of space-time white noise. Right. And so if now I have to think probabilistically, if I want to control this object, I can at least control the second moment of this random variable. And the question is, how do you control this norm, right? So this is an L2 space-time norm. It's an L2 norm in S and Y because those are my integration variables, and I'm integrating zeta in S and Y, right? And that's where this diamagnetic inequality comes in. The diamagnetic inequality is going to actually tell us, I mean, it's this amazing inequality where it just tells us that the B doesn't matter. In the sense that here, P is the usual heat kernel. It's the usual Euclidean heat kernel on the heat kernel on the torus. And there's this pointwise bound for this kernel here by the usual kernel. So this was, I mean, the consequence of this is that now I get a B independent bound. On the second moment. So if I use this pointwise inequality and I substitute it into here, I'm going to get that this is at most the L2 space-time norm squared of the usual heat kernel. But this is just, in a sense, the second moment of the usual object, right? Because if I did take B to be 0, then I just get the usual heat kernel because I just, if B is 0, this is the usual Laplacian. So then I just would have the usual heat kernel here. I should say that both sides, I mean, what I'm saying here is, you know, kind of, I mean, wrong because actually both sides are infinity. I mean, it's kind of trivially true. I mean, both sides are infinity because recall, like, this object is at negative regularity. And so point-wise, it's ill-defined. So kind of, it doesn't make sense to talk about the expectation of the modulus squared, but you always get around this by first smoothing a little bit and then taking a second moment. So I'm just going to ignore that for now. But I want to emphasize here that this was maybe one of our earlier aha moments where basically, we remove all dependence on B in our final bound. Like the right-hand side here does not depend on B at all, and that's very good for global theory. Because you want to, when you're controlling your solution, you want to kind of reduce the power of A as much as possible. So if A or B does not actually enter, that's really good. That's going to allow you to iterate. And so in the end, basically, I'm using this type of argument and then like making them, more precise. What you can actually show is that you can control this modified object in the right space, and you can control you basically have as much control as you want on it. It's like this is the same bound that basically the usual object satisfies. And that's the point. Like this modified object satisfies the exact same bounds as the usual one, uniformly in B. Right. So yeah, so that was one of our first main ideas, and maybe I should stop and see if there's any questions at this point. I know I'll probably finish up in like 4 or 5 minutes because I'm almost out of time. Okay, if there's no questions, then yeah, let me just try to wrap up. Right. So then now back to our original goal, which is stochastic Abelian-Higgs. We would like to take B to be A, right? Because that's what we want it to be, but there's problems with that. One of the problems is A and zeta are not independent. Like if we're gonna make this trick with this bound work, we at least need B to be independent of the driving noise. But that's not going to be the case because zeta is going to enter into A through some way. And so, okay, there's some obstruction to actually taking B to be A. And our workaround is kind of we take B to be the linear propagation of the initial data. And this leads to the following ansatz. We're going to take A to be like so. So this is the usual A linear object, which we call satisfies this equation. So, okay, I'm just writing it in small here. But this object here satisfies this equation. This B is exactly what I wrote here. And then Z is the remainder. So this Z is just whatever is the difference between A and these two terms. And then phi here now is going to be basically this object, which now gets B, where B is here, and plus a remainder of psi. And this is the final ansatz that's going to allow us to get global bounds. And basically, maybe this will be my last slide, and then I'll just finish. If you now write out the equation for Z and psi, as I did here, okay, again, it's like not so important what exactly the equations are. I just want to comment on 2 things. One is that the good thing about this now is that B squared does not enter. Like on the right-hand side here, whereas before I had like the A squared object, this no longer enters here. So that's good for us. That's the advantage of this, like this finer ansatz. Right. On the other hand, Z squared does, right? Because here I have Z squared now. Kind of before this was supposed to be A squared. Now the effect of this new ansatz is that I just don't have B here, right? So that's why it still wasn't clear to us at this point that we would be able to iterate this on a global time scale or on a unit time scale. But in the end, we're able to. I don't have a conceptual reason. We just had to write out the estimates, and everything just worked. And the thing that gives us hope, or gave us hope, was that Z actually starts at 0. Like because the point is that B gets the initial data of A, and so these things will have 0 initial data. And so the fact that Z starts at 0, even though it enters quadratically, ultimately allows us to iterate. I mean, it's again not clear, and it took us a lot of work to do so, but this was the starting point, basically. And then as a summary, I guess, the main ideas basically were that, again, geometry is informing singular SPDEs in the sense that we have to work more geometrically. We have to replace the usual linear object that you always do in local theory with a more geometric version. And the key thing was that the more geometric version still satisfies the same probabilistic bounds, it turns out, via the diamagnetic inequality. And then the second thing, which I didn't talk too much about, is that you still actually have to do analysis and bound everything. And you can get bounds on the remainder using some sort of what we call covariant monotonicity formula. Okay, but I won't get into details about that. With that, I'll finish, and thank you for listening.
So thank you very much for this beautiful and very clear talk. Are there any questions or remarks? Then please just unmute yourself and ask.
Yeah, can I ask a simple question? So,
Sure.
As for this black-headed tadpole, you had to consider this new covariant version, but you also had this white-headed tadpole. So, didn't you have to do anything for this? Probably.
Yeah, good question. So the reason why we don't do anything for that is because already in the equation, I mean, just the original stochastic equation, like the A equation is just the usual Laplacian.
No.
And so somehow it's more, this thing was the more essential thing, like because the fact that you have a geometric Laplacian here, that's why we replaced the kind of solid tadpole with this covariant version. But for the A, you don't have to because you just have the usual heat operator to begin with. Yeah.
Thank you.
Okay, then maybe let me ask a question. So I am mostly interested in this invariant measure. So how do you construct it? By the usual way of checking tightness?
Yeah, like Krylov-Bogoliubov, I would suppose. You basically get tightness from, I mean, basically the more refined version of our main result, which gives us uniform and time bounds on our solution. Basically, we can bound our solution at any later time in terms of the initial data and some constants. And from that, we just get tightness. Yeah. And so, I mean, we're not saying anything about uniqueness, of course, of the measure.
Yeah, that's why I'm asking.
Yeah.
Okay, but maybe you know something about non-Gaussianity?
Yeah, I mean, that's a good question. And you would think that we've discussed it, and there's probably a way to show non-Gaussianity using these PD techniques in the spirit of what they did for 543, showing, for instance, that you have like subcortic tails using the PD arguments. And you can try something similar like that here, which would definitely show non-Gaussianity. There might be more direct ways, but that's the way we kind of can see like more directly how one would go about implementing it. Although we haven't actually done it yet, but so some, yeah.
Okay. Any other questions or remarks?
I have a question.
Yes.
What about, can you do this kind of a proof with different gauges from the one you picked?
I don't. I mean, I don't know at the moment. Probably somehow no. At least, okay, right now I'll say no. Because somehow in this Abelian setting, the Coulomb gauge is just the best possible one. And so that's why, of course, it doesn't generalize to the non-Abelian setting, but as a short answer to your question, no, at least not right now.
Yeah, that's why I'm asking the question. If you could extend it a little bit to get other gauges, it might make your life easier when you try to do the non-abelian result.
Yeah, I certainly agree. And I mean, that's partly why non-abelian is a mystery, because it's all about choosing the right gauge. And we just don't know how yet. And I agree that maybe on this problem that we already know how to do, now we can try to not do the Coulomb gauge which won't generalize, but try something that will. But yeah, that's certainly a good thing to try. But yeah, at the moment we don't know how. Yeah.
I don't remember very well anymore, since, as you say, it was 40 years ago, exactly how we did everything. But besides the diamagnetic inequality, which you've highlighted, we also had bounds which were also called diamagnetic inequalities. They were basically bounds more connected with the invariant measure, and or even the normalization for the invariant measure. So if you have a Gaussian integral over A of a partition function for the Higgs field moving in the field A as if it was an external field, if you see what I mean. Does that make sense to you?
Yeah, let me try to write maybe what you're saying. So you kind of maybe if you focus on the phi field, you almost have like a GFF, but using a geometric Laplacian. Are you saying?
Yes, exactly.
And then if we just look at, I mean, without the polynomial thing, yeah, we would have like something like this as at least like if we look at this quantity. Yeah.
That's right, and you're integrating over the phi field. And
exactly.
the A has to be a little bit smooth for what I'm saying to work, I think. But there's another inequality, also called the diamagnetic inequality, which says that this Z sub A is less than Z sub 0 if you have periodic boundary conditions in all the directions.
Right.
And I can't remember whether we absolutely had to use that, but we certainly enjoyed having it as something to feed in at various places.
Right. I think it's related, the two diamagnetic inequalities, because this is kind of
well, the relation must be very subtle, because the proof of this inequality is Osterwalder. So we actually used it on the lattice, but then we can obtain it also for the continuum as a lattice limit, and it relied on Osterwalder-Schrader positivity. So it's not a natural property to use from the PDE point of view. And it would be good, in fact, if you could do everything without ever using it, but we found it useful.
Yeah. The way that, I mean, I haven't really thought about carrying this out, but kind of this partition function is, maybe I'll write it this way. So it kind of depends. It involves maybe something like the determinant of this covariant Laplacian, depending on A, I guess. I mean, right?
Well,
and then,
no, because you have the 5/4.
Okay. Yeah.
This applies when you can have any interaction any self interaction for the Bose field, for the Higgs field.
Okay, yeah, that's less clear then. Yeah. Right.
Anyway, it's very nice to see you people coming back to these problems after a long hiatus, and I'm very, very happy that you're making such good progress. Go for it.
Thank you. Yeah.
Okay, any other questions or remarks? Well, then maybe let me ask another question in the direction of constructing the quantum field theory, which is behind it. I guess you would need to take the infinite volume limit to really verify the Osterwalder-Schrader axioms, so try to verify them. So what about the infinite volume limit? Is it tractable in this case, or torus is important?
I mean, we don't know how to do the infinite volume limits at the moment. I mean, we had some discussions with some people that have tried, and I think there are some difficulties that you run into. Because, I mean, it didn't really enter into the talk, but if you want to prove more quantitative bounds in this soft thing that I talked about here, then it was kind of important to us that we can actually get decay for our solution. And somehow in infinite volume, the zero mode is problematic, I would say. We can handle it on the torus because it's just like discrete, but in infinite volume, when you go to Fourier, like the zero mode, I mean, it's continuous spectrum, and so that's kind of a problem with actually getting decay for our solution. So as a short answer, I think there are some problems. It's not just like an extension of what we did here, I would say. There are certainly new things to figure out to do the infinite volume thing.
Okay, I see. So, any other questions? Does not seem to be the case, so maybe it's time to move on to the informal parts of the discussion where often such questions come. So maybe let's thank our speaker again. And let me stop the recording.